Now let's talk about how to calculate magnetic field for a magnet. If we have a magnet with a magnetic moment M, then what's the magnetic field at, say, this position? All right, even though this question sounds so simple, but this question to calculate it, it's actually too complicated. You cannot really do it without some simplification and and high-end computer. So, well, yeah, this case is really beyond our ability for now. Another case which is simpler, for example, if I put a magnet here I put a north pole here and the south pole here. Then magnetic field will go from the north to the south. And because it's somewhat, like a uniform, so you can see the magnetic field here is uniform. In this case, I will just tell you the magnetic field here is, say, 1 Tesla going to the right. And then you will know that what I am saying is the magnetic field, because you can see the field line is uniform, so they all have the same magnetic field everywhere, and it's all 1 Tesla. Technically, there's nothing we can calculate for a magnet, but there's something we can do for an electromagnet. For example, if I have a straight wire with a current running through, and if you put a compass around this straight wire, you will see this compass will show up as this circular pattern, and show up with a circular pattern, and the direction of this circles is going clockwise in this case. So now if I ask you, hey, what's a magnetic field here? So to describe the magnetic field here, I will use this equation. So again, I apologize that I cannot really explain where's this equation coming from. It's coming from the idea of this magnetic field can be found by using Maxwell equation. But it takes some calculus to do it, so I'm gonna just skip that theory here. All right, so, but I can tell you what does this equation mean and how do you understand it. So the magnetic field at this position is basically depend on how far it is away from this current wire, okay, and how strong the current is. If it's a very strong current, then the magnetic field will be stronger. And if you are away from this wire, then your magnetic field will decrease. So basically, the magnetic field at this point is mu naught, which is a constant permeability, times the current, because it's proportional to the current, over 2 pi, and r. R is the shortest distance between the point to the wire. So this is R. This green line is R. So that will take care. So this equation will also call it Ampere's law, which take care of the magnitude. But how about the direction? If you put a compass here, where's this compass gonna pointing at? So to figure out the direction, we can figure out the direction with the rule. We call it right-hand rule. So specifically, I'm gonna call it right-hand rule 1. So right-hand rule is basically you have to, as for the name, you have to use your right hand. So now if you follow me, please do a thumb up, and your thumb, it must be perpendicular to this 4 fingers. Okay, so do a really good thumb up. And when you do the really good thumb up, the thumb will tell you the direction of the current. That's your thumb. And your four fingers, the direction of your four fingers will tell you the field. For example, if I have a current going this way, and then my thumb will, like my four fingers will naturally curl in this way, right? This four fingers I want to wrap around this wire, wrap around this current counterclockwise. Like counterclockwise. Okay. If it wants to counterclockwise, then that will tell you this straight wire current will create a circular magnetic field and going counterclockwise. Then you can also come back to see this picture. You see the current is going this way. So now you want to position your thumb in this direction and then curl your four fingers. Imagine there's a wire here. Okay. And now you can curl your four fingers. Then by curling your four fingers, you can tell like this is the current is going to the right, and where, and the how do I put this? Like the direction of the magnetic field will be going this direction. Okay. All right, now I'm gonna give you some practice about how to use your right hand rule. Okay. So for example, example one. Say if I have a current going to the left, then my question for you is, what is the direction of the magnetic field at this point? And what's the direction of a magnetic field at this point? All right, so this is when you want to use the right hand rule one. So again, do the thumb and you point your fingers towards the current. And then you can see your four fingers will do this, right? Will naturally curl this way. So imagine that you're holding this current, and then you can see that your finger one is pointing outward at B point, but inward at A point. So that is saying the direction of the magnetic field at A point will be into the page, and at B point will be out of page. And now I'm gonna give you another example. So say if your current is going into the page, say if I have a current, this is the head of the current, and the current is pointing into the page. Then what's the magnetic field look like at this four position? So now you take your right hand, do a thumb up, pointing into the page, and now your four fingers is showing you the clockwise, right? So that is saying that saying that the magnetic field at B position should be going upward, and A position should be to the right, and D position is downward, and C position is left. So basically, you will create a circular magnetic field going clockwise. Does that make sense? All right. And you can also elaborate this question to say if I have two currents, these two currents are the same. What's the magnetic field at the center? What's the direction of it? So let's see, if I have a current here going this way, then this current will create a magnetic field into the page at this point, right? You see that? It's curling this way, so it will be into the page at this point. So that's from this current. And now if we look at what does this current do, this current will also create a magnetic field. And you can do the thumb up and do this. So you can see your four fingers is telling you, the four fingers is telling you magnetic field at this position should be out of page. Oh, I drew this wrong. Sorry, this was into the page, right? And the red current will make it out of page. So since these two currents, both of them contribute some magnetic field at this position. So the total magnetic field will be the field coming from here. That's into the page. And the field coming from here. That's out of page. And I'm going to say, assume, I'm gonna just conventionally, we will assume that outer page is positive, into the page is negative, just like right is positive, left is negative. So now I have this. So this magnetic field coming from here will be negative, and another one will be positive. So eventually you can see that it turns out to be zero. So the magnetic field in the center of between these two wires is zero. We can also wire our current into a loop, like the solenoid case that we just talked about. So it's gonna be a loop. If we wire the current into a loop, then things will become a little bit complicated, right? Because you see the magnetic field is not uniform everywhere. So this yellow-orange ring, it's a current loop. You'll have a current running counterclockwise on this loop. And usually, technically, you have magnetic field everywhere, but all those magnetic field will need some integration to figure out the strength. But this point is particularly simple. So the magnetic field for this point is just B equals to mu naught I over 2R. So this equation is coming from, integrating all the, because all of this little current segment, they all have create a magnetic field at the center. When you sum them up, this is that result. And it looks like this. So I'm gonna tell you like how to picture this formula so that you can have it clearly in your mind. So first, this magnetic field at the center must depend on the current. If you have a very strong current, then the field in the center will be stronger. And for R, if R is greater, which means the ring is away from the center. If the ring is away from the center, then the magnetic field created by the ring at the center will also be weaker. So R here is the radius, and where I is the current. So that takes care of the magnitude. Now you probably want to understand what's the direction of the magnetic field in the center. To understand magnetic field at the center, I can still use my right-hand rule 1. So, but now my current is has all kind of different directions. So let me just pick a point and go from there. If you put your hand here, your thumb pointing at the current direction, your 4 fingers will want to, kind of curl back, right? Kind of want to curl back like this. 4 fingers, so it should go like this. Your finger want to curl back, right? If your finger want to curl back, you will if you try it out by yourself, you can see that magnetic field at the center, due to this current, should be going upward. Then you can move your hand over, and your current will now go in this way. And if your current now going this way, your 4 fingers will curl up this direction. your four fingers will curl up this direction, right? If your four fingers curl up in this direction, magnetic field at the center caused by this current will be like here, right? It's tangential line. It will be going upward. So it's upward again. Then you can do the same thing. You can move your hand over and do the same thing. Then you'll realize that it's also providing a magnetic field going up. So when you add up all this magnetic field, they're all constructive. So it will just all add up. They will add up and give you this magnitude. However, so add up to be this magnitude, and the direction has to be up, of course, because each individual contribution contribute upward. So the total is also upward. And then you can use the same idea. So imagine now if I have a lot of loops. If I have so many loops, the loop is so many up to a point that it's so dense that it will just behave like a magnet. Remember we did a simulation in the video about this solenoid, this shape of current. Well, solenoid shape of current, it basically behaves like a magnet. You can see you can see this picture. This is a magnet picture. This is a solenoid picture. You see their magnetic field almost look identical. And since the magnetic field looks almost identical, then of course a magnetic field outside of this solenoid will be too complicated to calculate. So we are not gonna do that. And what we can calculate is, again, just like a ring. We can calculate the magnetic field inside the solenoid. When this solenoid is long and very dense, you can imagine the cylinder is holding a lot of magnetic field line and then push them together. So if you really look at it, you will see this magnetic field line, they are somewhat uniform distributed inside this solenoid. So the magnetic field line inside the solenoid will be uniform, and the magnitude of it is described by mu naught in I. So first, if you have a stronger I, you have stronger current, you will create a stronger field. That makes sense. If you have more loop, if you have more loops per unit length, basically you have more contribution from the current. So that will also increase your magnetic field. You can see that R does not really, the radius doesn't really play a role anymore because you see that's what I'm saying. Like if you have a lot of them, like it's like holding all the lines together, so it becomes uniform. And if it's uniform, then R doesn't matter. If you want to know what's the direction of the magnetic field line inside the solenoid, if you want to know the direction, you can also just apply the same logic as in the loop, because it's essentially a collection of a lot of loops. So in this case, it will be going upward. Okay. So okay. So that's it. Basically, that covers all the structure. But up to this point, there's one more thing I want to tell you. It's about this right-hand rule. So many different people have different flavors on right-hand rule. Some people will use different hand gestures, even though we all eventually come to the same conclusion, but the way to do it could be different. So for example, the way I'm introducing you here, this right-hand rule might be different than the Khan Academy or in the OpenStax. But I just want to let you know, all rules, like always, are correct. Like all different hand gestures, they are probably all correct. But we just kind of do it differently. So if you learn it from one side and you feel like, oh, why the hand gesture is different than another side, don't panic. Just make sure that you do understand what you're doing, and that would be good. So following along that line, generally, I just want to introduce one right-hand rule in this unit, but now, because later on you will find another right-hand rule could be useful. So here I'm gonna introduce you the second right-hand rule. So the first right-hand rule is applicable for all the current-induced magnetic field, and the second right-hand rule only works for a loop. So this is the second right-hand rule. Right-hand rule 2. So remember, like if I want to figure out the direction of the magnetic field in the center of a loop or of a solenoid, what we have to do is we need to pick one point of the current and keep doing the first right-hand rule to help you understand the direction. But the second right-hand rule is also very, it's another rule that which can also help you figure out the direction of the magnetic field inside a solenoid. So this is how the second right-hand rule works. So again, you wanna do a thumb up, and where your thumb now is the magnetic field, and your 4 fingers is the current. This right-hand rule is saying if you have a solenoid or a loop, you can use your 4 fingers to mimic the current. So for example, the current in this way is going this direction, right? So you can just like use your hand to hold. Imagine that you're using your hand to hold that bar, following the direction of the current. And when you do that, your thumb will naturally pointing to the left. And that is telling you the magnetic field in the center of the bar is to the left. So you can see the right-hand rule 1 and right-hand rule 2, they flip the position of the B and I. But right-hand rule 1 it can be used for any current, while right-hand rule 2 can only be used in a loop, like a current wire, or like solenoid type of a current wire. All right, so now I'm gonna give you some examples on a loop like a current. So for example, if I have a ring like this and the current is going this direction. Okay, so when I draw this one, because it's like a simple diagram, you probably cannot really see that in the 3-dimensional. So what I'm gonna do is I'm gonna draw its cross section. So say I cut a cross section here. Okay, in the middle. This is a ring. I cut it in the middle. And if I cut in the middle, I can draw this in the 2-dimensional like this. I'll see this is my loop. It's an edge-like view. And on this side, this is my ring, right? The ring. And the current is going this way, right? So if I look at its cross section, you can see the current at this point should be going out of page. And the current at this point, because the ring goes like this, the current at this point will be into the page. So when I draw a bar with the dot here and the tail here, and I tell you this is an H view, this is what I mean. I mean, I position my current, the ring of the current in this direction, and you're looking from this H view. Okay. So now my question is, what's the magnetic field at the center? The magnetic field at the center from this equation, I know it's going to be mu naught. So I'm going to say this is R, current is I, mu naught I over 2R. And how about the direction? So the ring is this, right? The ring is this. Current is going this way. So now I'm going to use my right-hand rule 2 And again, right hand rule 2, your thumb is field, your fingers is the current. So now I'm gonna use my 4 fingers to curl this current. The current is going this way, right? The current is going this way. And my thumb is telling me the magnetic field in the center will be going upward. So the magnetic field in the center will be upward. If you don't want to use the second right hand rule, you can use the first right hand rule and to do this, and then that will also give you the same answer. Okay. So one more practice. Say if I have a solenoid, a lot of loop, and the current they are all going in this direction. Then what's the magnetic field at the center? So the B naught, the B field, magnetic field at the center will be mu naught n I because it's a solenoid. And then how about the direction? So now again, I want to use right hand rule 2. We have 4 fingers curling this way, which is a current, which curling this way. So if my 4 fingers curling this way, then my thumb will be, you see, my thumb will be into the page. So the magnetic field at the center will be this and into the page at this point.